All right, folks, we are back, section 4.333, studying iteratively reweighted least squares. Now, it took me an extra week to make this video, and the reason why was, although everything in this section is correct, it's a lot of kind of turning the crank, and there's no insight into what's going on or where the expressions come from. So I spent an extra week trying to really dig into it and trying to understand what's happening with this algorithm, how it actually works, instead of just getting the values out. And so what I'm going to do in this video is we'll just go through the section, we'll discuss what's there, and then in the next video we'll go through my notes on the section and I'll tell you kind of what's really going on, where the expressions come from. Okay, so with that, let's get started. The section is pretty simple. So the first thing we're going to talk about is Newton updates. So using second order information, curvature information basically, making a quadratic approximation to your function in the hopes of converging faster. So not just using gradient information, but curvature information. Then he kind of applies this to the regular kind of sum of squares error function that comes up in linear regression. We see that the updates happen in one step because the surface there is quadratic. So when the surface is quadratic, the Newton update gives you the solution in one step, because its model of the function matches the function itself. But in general, that won't be the case. So so we'll just see what the updates look like. When that's not the case, we'll find the updates for logistic regression, and we'll get this expression out, and well, that's the answer. And because the curvature is changing with our loss function, it's not always the same quadratic. We just apply this update over and over again, and we arrive at this iterative reweighted least squares algorithm, which is kind of the focus of the section. And then he'll kind of give some kind of spurious interpretation of where some of these terms come from, which is kind of what started me on my search of trying to understand what's really going on. I'll talk about where that comes from, but in the next video, I think I'll give you a better way of thinking about what's going on with this algorithm. Okay, so let's get down to it. Okay, so he says, in the case of the linear regression models discussed in chapter 3, the maximum likelihood solution on the assumption of a Gaussian noise model leads to a closed form solution, right? So we could there was just a formula we got for getting the parameter vector. And it was a consequence of the quadratic dependence of the log likelihood function on the parameter vector. For logistic regression, there is no longer a closed form solution due to the nonlinearity of the logistic sigmoid function. Okay, so we're not going to get the closed form solution, but maybe we can get something that's close enough. The departure from a quadratic form is not substantial, and the error function is concave. So that means it's just going to look like this. So so concave could mean, it basically means that you're not going to have kind of funny shapes like that where where some of the chords will go below the function. So it'll kind of be well behaved. And therefore has a kind of a unique minimum, and the error function can be minimized by an efficient iterative technique based on the Newton-Raphson iterative optimization scheme, which uses a local quadratic approximation to the log likelihood function. Okay, so what was this about? This was essentially the idea of how you got your function like that. Maybe let's make it a little bit more, I don't know, whatever it is, and we'll make kind of a local quadratic approximation to it, and we'll update to the bottom of that approximation. So we'll just assume that, okay, our function actually is quadratic, and then we'll start again. And the form of the function, what you do is you essentially find a change to your current parameter values so that the gradient of your function is 0. So let's see how we do that and where we get this from. So the idea is, if you guys know about Taylor Taylor decomposition, a Taylor series. So we say the same. We're looking at the gradient of our function at some point w plus delta w, and we know that this is going to be equal to approximately the gradient at w plus the curvature of E at w times, okay? And now we just set this to equal to 0. So we're trying to essentially find, using just the curvature information and our gradient, find the delta so that the gradient at this approximation equals to 0. So if we do that, well, we just simply get you guys can see this, times delta, I'm sorry, I should say, the gradient at w times delta, is equal to minus, and so that goes to the delta is equal to minus the inverse of the curvature times the gradient. Okay, so then you just say, well, this is equal to w new minus w old equals all of that, and from that you get the update above. So this would be your curvature function, and this is your gradient. Okay, cool. Good. Okay, so that's where that comes from. So that's all you're doing. You're essentially just making this quadratic approximation and updating your w as if that approximation was exact. Okay, so now we're going to apply it to, let's erase all of that. And now we're going to apply it to the linear regression loss function. Okay, so let us first of all apply Newton-Raphson method to the linear regression model with the sum of squares error function. The gradient, so this was just, remember what the loss was, so E of w in that case was the sum on n of t of n minus phi of n transpose w squared n of the 1/2. Okay, so if you work out what the gradient is, you'll see that it comes out like this. We find out what the curvature is. Hessian, notice that it's constant in our features. Sorry, in our parameters, because there's no w's in here. So this is kind of a constant curvature. Well, what shape has a constant curvature? A parabola, and so our quadratic approximation is going to be exact. And so you guys can see this. So where phi is the n by m design matrix, with nth row is given by so and so. And now the Newton-Raphson update then takes the form, we just plug in those values above, and notice that things cancel out in such a nice way that we just get a single update. So there's no w's here. There's no w's here. You just get the solution. You can jump immediately to the bottom of this parabola, which actually defines your error function. So we recognize it as a standard least squares solution. Okay, so that's another way of looking at least squares. Note that the error function in this case is quadratic, and hence the Newton-Raphson formula gives the exact solution in one step. So that's kind of the ideal setting. So now let's apply the Newton-Raphson update to the cross entropy error function for logistic regression. Okay, so if we just if you plug it in, we go through, we see the gradient of the Hessian. So the cool thing about logistic regression with the logistic sigmoid is that the gradients and Hessians and things have some nice properties to make things cancel out really nicely. So we see that the gradient and the Hessian of this error function are given by, so it's the features times the difference between your outputs and your targets. That's quite nice. Like in general, it won't happen so nicely. And the Hessian is, well, the Hessian with your features, but now you're weighted by these terms that depend on what your output is. You can think of these as the variances of your outputs. And so you can kind of pack them up into this matrix here. So it's like the one we had before, but now you've got the variances, R1 all the way to Rn for each of your outputs, each of the observations. Or we have made use. Also, we've introduced, the dot I just told you about this. We see the Hessian is no longer constant, right? So we don't have. If we had a quadratic, it would be constant everywhere. It would be like what we had before, phi transpose phi. But now we've got this dependence on location through this R, this diagonal matrix. It's kind of scaling the elements. Depends on W through the weighting matrix R, corresponding to the fact the error function is no longer quadratic. Using this property, which follows from the form of the logistic sigmoid, this is positive, this is between 0 and 1, this is between 0 and 1, so the thing will be 0 and 1. We see that for any vector u, the Hessian, if you multiply by the Hessian on both sides, it'll be positive. So this means that the Hessian has all positive eigenvalues, so its H is positive definite, and it just means it's just concave. That's literally what it means. It means the curvature is always increasing in every direction, so your function is well behaved, and it looks like a cup basically. Even though the curvature will be different at different points, it still looks like a cup. It follows that the error function is a concave function of W and has a unique minimum. Okay, so that's good. That's a really nice situation to be in. You can find a solution. You don't have to worry about multiple minima. There will be a minimum. There won't be like local maxima, local minima, etc. It's a nice situation to be in. Okay, but again, we don't have, it's not exactly a quadratic, so we're just going to apply the Newton-Raphson formula to make local quadratic approximations and update. When we just literally just we plug in the formulas that we had, so we get the new, the delta W is, we've got the curvature, so this is the curvature here, the inverse of the curvature, times the gradient. And we can kind of rearrange this, and we see that, okay, so it actually turns out to be a weighted least squares projection of some value z. So this is, when we'll talk about this in the next video, but the idea with weighted least squares is, the projection you do when you weight some of your observations more than the others. And the form of that, so the ordinary, when everything is weighted the same amount, these are all gone. These are just identity, and we got our normal least squares projection. But when you have this weighting, it kind of shows up in places like this. So we're somehow doing a weighted least squares projection of some value z, and that has this form. Why does it have this form? We're not really told. Okay, he kind of makes a guess at what it's about. Not a guess, he makes a statement about what it's about. But I don't think that's the right. His solution is not going to be the right way of thinking about it. Okay. But anyway, so we've just kind of turned the crank here, rearranged some things, and we see, hey, look, we see the update formula takes the form of a set of normal equations for a weighted least squares problem. Okay, why does it do that? There's no comment on this. Because the weighting matrix is not constant, but depends on the parameters, we must apply the normal equations iteratively. Okay, so we keep doing this again and again, each time using the new weight vector to compute a revised weight matrix R. So you just keep doing this, update your W, get some new outputs, update your R, and keep going until you converge. For this reason, the algorithm is known as iterative reweighted least squares. As in the weighted least squares problem, the elements of diagonal weighting can be interpreted as variances because the mean and variance of t in the logistic regression function are given by this. So the variance, we already talked about this, the variance of the outputs has the form, and those are what's in the columns of R. Okay. In fact, we can interpret IRLS as a solution to a linearized problem in the space of the variable. Remember this is how we linked our features into what was going into the sigmoids. And the quantity z of n, which corresponds to the nth element of z, can be given a simple interpretation. And I just think this is the wrong interpretation to be using. By making a local linear approximation to the logistic sigmoid around the current operating point. Okay, and so the way he does it, he comes up with this formula and says, hey, look, this is equal to, this is explanation for what it is. I actually think this is not a good explanation, but I'll tell you where this comes from. So basically the idea is, you've got some targets t, and we can just do it for a single variable. And we want to say, well, this is going to be equal to sigma of the weight, it's going to be A, our current value, again, plus some delta, okay? We want to set the delta, such that this condition holds, so that our outputs are the ones that we want. Well, so this is going to equal to sigma A plus times d sigma dA, right? So this is just going, so this, oops. Sorry, that's what I already had. D sigma dA times delta. And then, so from this we get t minus sigma over d sigma dA is equal to delta. And so this is just the same as t minus sigma times dA over d sigma, because seeing they're so well behaved that the inverse of the derivative is the derivative going the other way around. So the derivative of the output relative to the input. And that's exactly what we have here. So that's basically this. That's how you come up with it. But I believe this is just, so I've looked at it, and this is just a coincidence. It only works for the logistic regression with the logistic sigmoid in it. And I don't think this is the right way to interpret it. So in the next video, I will show you kind of what I think is actually going on with logistic IRLS applied to logistic regression and the right way to interpret this Z term. So yeah, so I think this section was, a lot of turning the crank. You get the updates, great, but there's no insight. I'm hoping in the next video I can give you some insight for what's actually going on, and I hope you'll join me there. Bye.